Welcome to the course on an introduction to information theory. I am Adrish Banerjee. So far we have studied block to variable encoding and variable to block encoding. So today let us try to solve some problems in source compression. The first problem relates to Huffman coding. So there exist several fundamentally different optimal prefix-free code. Now we know Huffman coding is the optimal prefix-free code. So there exists several fundamental different Huffman code. And what do I mean by fundamentally different? If I write down the code word length, ordered list of code word length, that is different. Okay. So when I say fundamentally different optimal prefix-free code, I mean these are Huffman codes, and if I arrange the Huffman code by the length of the code words, their ordered list of code word length is different if they are fundamentally different optimal prefix-free code. So the question is, how many fundamentally different optimal binary prefix-free code exist for a random variable which has following symbol probabilities given by 0.3, 0.2, 0.2, 0.1, 0.1, 0.05 and 0.05. So this random variable takes 7 different values and these are the probabilities associated with it. The question is, you have to construct optimal binary prefix-free code and you have to tell how many fundamentally different optimal prefix-free code exist. So we know how to construct optimal prefix-free code. We know the properties of Huffman code. Recall that if it's a binary optimal prefix-free code, the two least likely code words, they differ in only 1 bit location and there is no leaf which is unused. And if you recall, the way we proceed is we start with 2 symbols which have the least probability, we join them, create a new node, deactivate those old nodes, and this new node is now, it has probability equal to some of the probabilities of those old nodes. So this way we at each step we combine the 2 least likely nodes until we are left with only 1 node, which is the root node. So we will do that and we will see how we can get different fundamentally different optimal prefix-free code. So in this example, these are the probabilities of UIs: 0.05, 0.05, 0.1, 0.1, 0.2, 0.2 and 0.3. So first we are going to combine these two. Okay, so we combine these two, we get here, we create a new node which has probability of 0.1 and we deactivate these 2 nodes. Okay, so at this point we have now, these are the active nodes, this one, this one, this one, this one, this one and this one. Now note, we have 3 nodes and leaves which have probability 0.1. This one and this one. So we could either combine these 2, we could combine these 2 or we could combine these 2. So in this case I am just combining these 2. If I do that, I create a new node which has probability given by 0.2 and I deactivate these 2 nodes. So at this point my active nodes are this one, this one, this one, this one and this one. Now I have this as probability 0.1, this is 0.2 and this is 0.2 and this is 0.2. So I could combine this with this, I could combine I could combine this point 1 with this point 2, or I can combine this point 1 with this point 2, or I can combine this point 1 with this point 2. So there are 3 point 2s, this one, and this one. I could combine this node which has probability 0.1 with any of these 3 nodes. So in this example, I'm just combining with this one. Okay, so I get a new node whose probability is given by 0.3, and I deactivate this node, I deactivate this node. So at this point, my active nodes are this one, this one, this one, and this one. And what are the probabilities I have? I have 0.3 here, 0.2 here, 0.2 here, 0.2 here, and 0.3 here. So again, note that I have 3 nodes which have probability 0.2. This one, and this one. So I can combine any 2 of them, right? So in this case, I'm combining this with this. So then I create a new node which has probability 0.4, and I deactivate this node, and I deactivate this node. Now at this point, my active nodes are this one, okay, this one, and this one. So these 3 are my active node. So now I have this node probability 0.3, this node probability 0.3, this node probability 0.4. So I'm going to combine these 2 nodes. And this has my probability 0.6, and finally I deactivate these 2 nodes, so I'm left with only 2 active nodes. One is this one, another is this one. So I combine both of them. And the final step is I assign zeros and ones to these branches, zeros and ones to these branches. So if I do that, what I come out with is the code word for this particular symbol is 10. This you can see 10. Code word for this comes out to be 00. You can see 00. And similarly, you can find out code words for other. This is 110, 110, 011, 1110, and 1111. So this has code word length 2, 2, 3, 3, 3, 4, 4. So if I write the ordered list of code words, I have 2 of them with length 2, 3 of them having length 3, and 2 of them having length 4. Now let us look at another way in which we can construct this optimal binary prefix-free code. So same example. So the 2 smallest probabilities are 0.05 and 0.05. So we can combine these 2 and create a new node which has probability given by 0.05 plus 0.05, that's 0.1. We deactivate this node and activate this new node. So now we have this node which has probability 0.1, this node probability 0.1, this node probability 0.1. So we can combine any 2 of them. So let's combine these 2. See, combine these 2, we get a new node with probability 0.2. We deactivate this node, we deactivate this node. So now the active nodes are this one, this one, this one, this one, and this one. Now we have one node with probability 0.1, which is this one, and there are 3 nodes with probability 0.2, this one, and this one. So we have to combine this leaf which has probability 0.1 with any of these leaves or nodes which has probability 0.2. So let's say we combine these two, we get a new node which has probability 0.3, we deactivate this two leaves. Okay. So then what are the active nodes at this point? This one probability 0.3, this one probability 0.2, this one probability 0.3, and this one probability 0.2. So we combine these two nodes which has probability 0.2, get a new node with probability 0.4, and we deactivate these two nodes. Okay. So now we have this active node with probability 0.4, this active node with probability 0.3, and this active node with probability 0.3. So we combine these two nodes, create a new node with probability 0.6, and deactivate these two nodes. So now we have two nodes left, this one with probability 0.6 and this one with probability 0.4. We combine them and we make this as a root node with probability 1. And finally we assign zeros and ones to these branches, right? We assign zeros and ones to these branches. So if we do that, we get the code word for this particular symbol as 0, 0, for this one 1, 0, this one 0, 1, 0. Again you can check. For example, let's go this is 0, then this is 1, and this is 0. That's why you're getting 0, 1, 0. Code word for this is similarly 0, 1, 1, this one 1, 1, 0, this is 1, 1, 1, 0, and this is 1, 1, 1, 1. So we have this code word of length 2, 3, 3, 3, 4, 4. So the ordered list of code words. So we have two code words of length 2, three code words of length 3, and two code words of length 4. Now if you compare with previous Huffman code, this also had two code words of length 2, three code words of length 3, and two code words of length 4. So this is not fundamentally, so the code tree 2 is not fundamentally different from code 1, because if I write down the ordered list of code words, though this mapping is different, but it's not fundamentally, they have the same set of ordered code word. Now let's look at another way of combining these nodes. So again we start off with these two nodes which have the least probability. So we combine them, create a new node which has probability of 0.1. We deactivate these two nodes. Next we have this node with probability 0.1, this particular leaf with probability 0.1, and this node with probability 0.1. So we can combine any two of them. If we combine these two, we get a new node which has probability 0.2. We deactivate these nodes. So at this point our active nodes are this one with probability 0.1, this one with probability 0.2, this one with probability 0.2, this one with probability 0.2, and this one with probability 0.3. So I combine the 0.1 with any of the leaves or nodes which has probability 0.2. In this case I am doing with this one. So what I get is a new node with probability 0.3, and I deactivate these nodes. So at this point my active node is this one with probability 0.3, this one with probability 0.2, this one with probability 0.2, and this one with probability 0.3. So I combine these two which has the least probability 0.2, 0.2, and get a new node which has probability 0.4. I deactivate these nodes. So my active nodes here is this one with probability 0.3, this one with probability 0.4, and this one with probability 0.3. So again combine these two nodes, I get a new node with probability 0.6, and I have another node with probability 0.4. I join them and create my root node which has probability 1. Now if we look at the code words here, again we label each of these branches by 0 and 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So you can see code word corresponding to this is 1, 0. Code word corresponding to this is 0, 0. This one code word is 0, 1. So similarly you can find out this one has code word 1100, 1101, 1110 and 1111. So you can see I have 3 code words of length 2 and I have 4 code words of length 4. So if I write the ordered list of code words in terms of their length of the code word, you can see that this particular optimal Huffman code, its ordered list is different from what we got in the earlier 2 cases. So this prefix-free code, optimal prefix-free code, is fundamentally different from what we have got in the previous examples. There is another way in which I can combine these symbols with this probability, and look at this. So again start off with the 2 least probable leaves. So this has probability 0.5, this has probability 0.5. I combine them, get a new node with probability 0.1. I deactivate these 2 nodes. So this one and this one, they have probability 0.1. I can combine any 2 of them. Let's say I combine these 2. So I deactivate these 2 nodes and create a new node with probability 0.2. So what are my active nodes at this point? I have this one with probability 0.2, this one with probability 0.1, this one with probability 0.2, this one probability 0.2, this one with probability 0.3. So I need to combine this particular node with any node which has probability, any node or leaf which has probability 0.2. So if I combine this with this, I create a new node with probability 0.3. I deactivate these 2 nodes. So at this point then my active nodes are this one with probability 0.3, this leaf with probability 0.2, this one with probability 0.2 and this one with probability 0.3. So I combine these 2 together because these are the 2 least likely active nodes and create a new node which has probability 0.4. I deactivate these 2 nodes. So now I have an active leaf with probability 0.3, an active node with probability 0.4, an active node with probability 0.3. So I will combine these 2 which has probability 0.3, create a new node which has probability 0.6, and finally I combine my active nodes. So I deactivate this and this. So finally my active nodes are this one and this one. So I combine these 2 and what I get is a root node with probability 1. And finally, as I said, I am going to assign zeros and ones to these branches. 0, 1, 0, 1, 0, 1. Now you can see code word for this is 1, 0. Code word for this particular symbol is 0, 0. Code word for this is 0, 1. Code word for this is 1, 1, 0. Code word for this is 1, 1, 1 and 0. Code word for this is 1, 1, 1, 1 and then 0. And finally this one is 1, 1, 1, 1, 1. So now I have 3 code words of length 2. I have 1 code word of length 3. I have 1 code word of length 4 and I have 2 code words of length 5. So this is also a fundamentally different optimal prefix-free code. Please note these all the different ways in which we are combining these nodes. We are essentially following the rules of how to create this optimal binary prefix-free code. So you can see from this example there are fundamentally 3 different ways in which you can have the ordered list of code words length. For code 3, 1 and 2 we had this particular ordered list. For code 3, 3 we had this, and for the code 3, 4 we had this one. So you can see for a source which emits this 7-ary random variable with these probabilities, there are fundamentally 3 different ways in which we could create or we can construct optimal binary prefix-free code. Okay. Now let's move to a next example. So this is also a problem related to Huffman coding. So we have a Y16 batch which is going to represent IIT Kanpur in an inter-IIT chess meet. Okay. And so the captain Vipul found out that these are the best student in terms of representing the IIT team, and he organized a chess competition where they played against each other, and he found out that these are the corresponding probabilities of their winning against each other. So Saurabh won 1/3 of his match, Arjun won 1/3 of his match, Amrita won 1/9 of her matches. So these are the probabilities of their winning the match when they played against each other. Now Vipul wants to convey this information to his coach Adrish, who is vacationing in Kullu. Okay, so he has to transmit this information to his coach. So he has to communicate essentially that these are the probabilities of winning of each of these team members. He wants to convey these probabilities. So essentially we have a random variable which has 7 possible values. So I mean 2 of them can take, so he wants to communicate. So U1 happens with probability 1/3, U2 happens with probability 1/3, U3 happens with probability U3, U4 happens with probability 1/9, and U5, U6, U7 happens with probability 1/27. Now he wants to encode this information using an optimal block to variable length coding. Now there are 2 telegraph services in the campus. One is known as Ajit Speedy Post and other is Ketan Super Services. Now Ajit Speedy Post transmits binary bits and it charges 40 rupees per binary bit, whereas Ketan Super Services charges 65 rupees per digit. Now what Vipul has to do is he has to select one of these telegraph services. He has to either select Ajit Speedy Post which sends binary bits and charges 40 rupees per bit, or he has to choose Ketan Super Services which transmits ternary bits and charges 65 rupees per ternary bit. So what service should Vipul use to communicate this information to his coach Adrish, and what is the expected cost? So that is the first question. And second question is, if Kaitlyn Super Services decides to increase its charges, at what new rate Vipul will change his mind? So this is a problem statement. So clearly one services uses binary bits, other uses ternary bits. So Vipul first has to create an Huffman, because he is using block to variable encoding to encode these probabilities. So in first case he has to construct a binary Huffman code. In the second case he needs to construct a ternary Huffman code, and then he needs to find out what is the expected code word length in these two cases, and he has to multiply them by their average cost. So that would give him the total expected cost. So let's look at first binary Huffman tree. So we have nodes which have probability 1 by 3, 1 by 3, 1 by 9, 1 by 9, 1 by 27, 1 by 27, and 1 by 27. So first we are going to combine these two nodes, right? We get probability 2 by 27. Then next we need to combine these two nodes. We'll get 1 by 9. Okay, we can combine, let's say, these two nodes, which will be 2 by 9, right? Then we can combine these two nodes, which will be give us 1 by 3, and we can combine these two nodes, which will be 2 by 3. And finally we can get this. So if we, this is probability 1, and if we assign zeros and ones here, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So this code word corresponding to this will be 0, 0, this will be 0, 1, this will be 1, 0, 0, 1, 0, 1, this will be 1, 1, 0, this will be 1, 1, 1, 0, and this will be 1, 1, 1, 1. Right? Now we can do the same thing in another way. So both will essentially give the same expected value. Let's try doing the same thing in another way. So let's see, we have this 1, 3 code with probability 1/3, no leaf with probability 1 by 9, and then we have 3 nodes with probability 1 by 27. So I start off with these two nodes, make a new node which has probability 2 by 27, then I combine these two, I get a new node which has probability 1 by 9. I can combine these two nodes, get a new node with probability 2 by 9, and then I can combine these two, I get a new node which has probability 1 by 3. I can combine these two nodes, get a new node with probability 2 by 3, and then I can combine these two, get my root node with probability 1. Now if I assign bits zeros and ones, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So this will have code word 0, 0, this will have 0, 1, this will have 1, 0, this will have 1, 1, 0, this will have 1, 1, 1, 0, this will be 1, 1, 1, 1, 0, and this will be 1, 1, 1, 1, 1. So there are multiple ways in which I can create this Huffman tree. Each one of them will give the same expected value. You can verify that. And what I have written here is actually this one. Okay. Now you can find out what the expected code word length is. from path length lemma. The expected code word length is nothing but it is the sum of probabilities of all the nodes including the root node. So this is 1 plus 1 by 3 plus 2 by 9 plus 1 by 9 plus 2 by 27 plus 2 by 3, which comes out to be this 2.4. We can calculate the same thing. From here we will get the same answer. You can verify 1 plus 1 by 3 plus 1 by 9 plus 2 by 27 plus 2 by 9 plus 2 by 3 will get the same. So the expected code word length, if we use a binary Huffman code, is going to be 2.4 bits. Now what was the cost of Ajit's speedy post? It was 40 rupees per binary bit. So if you multiply it by 40, we are going to get the expected cost if we use Ajit's speedy post. So the cost involved if Vipul uses Ajit's speedy post is 96.3 rupees. Okay. Now let us look at Kaitlyn Super Services. Now Kaitlyn Super Services uses ternary bits, right? And we have u which takes value 1 by 3, 1 by 9 and 1 by 27. Now, so k in this case is 7. What is d? It's a ternary code, so d is 3. So first thing we need to find out at the initial stage how many unused leaves are there, and how do we find out that out? K minus d into d minus 2. If we divide this by d minus 1, whatever remainder is remaining. So k minus d in this case is 4 and d minus 2 is 1. So 4 divided by 2, remainder is 0. So there are no unused leaves if we use this particular source and encode it using ternary Huffman code. So then in the initial stage we are going to combine 3 of these leaves. So these are the 3 least likely leaves. So we combine them, and this will have probability equal to 1 by 27 plus 1 by 27 plus 1 by 27. So this is probability is 1 by 9. Next we combine this node and this node, and their probability is 1 by 9, 1 by 9 plus 1 by 9, that's 1 by 3. And finally we combine these 3 nodes. This is root, this probability 1, and if we assign 0, 1, 2 to these branches, so I get the code corresponding to this is 0, code corresponding to this is 1, code corresponding to this is 2, 0, code corresponding to this is 2, 1, code corresponding to this is 2, 2, 0, 2, 2, 1 and 2, 2, 2. So again I can find out the expected code word length using path length lemma. So it is sum of probabilities, sum of the probabilities of all the nodes including the root node. So this will be 1 plus 1 by 3 plus 1 by 9, and that comes out to be 1.44 bits. Now Kaitlyn Super Services charges 65 rupees per ternary bit. So if I multiply 65 into this expected code word length, the cost that comes out is 93.88. And what was the cost for Ajit's speedy post? It was 96.3. So that is more. So Kaitlyn Super Services is cheaper. So Vipul is going to use Kaitlyn Super Services. The next part of the question was by what price if he increases Kaitlyn his charges, at what point Vipul will change his decision. So that we can calculate. So we know the expected code word length for ternary, which is 1.4444 into cost, let's say cost is rupees X. That and the cost of binary transmission is 40 and number of bits for 2.4. So if you from here you can find out what is the break even cost. If Kaitlyn increases the cost beyond this point, then Vipul is going to change its decision, and that price comes out to be 66.67. Okay, so if Kaitlyn increases his cost of his ternary transmission of ternary bits more than 66.67 per ternary bit, then Vipul is going to change his decision and will go for Ajit's speedy post. Okay. Now next we are going to prove some result of a binary Huffman code. So prove that if you have a binary Huffman code and its most probable symbol has probability which is given by less than 1/3, then this symbol must be assigned a code word length of at least 2. So if the most likely symbol has probability less than 1/3, then you must assign this most probable symbol at least a code word of length 2. Now how do we prove this result? So we will use the method of contradiction. So we will say, let us say that we are assigning this most probable symbol which has probability less than 1/3. We will assume, let's say we are assigning it a code word of length 1, and then we will show that this is not possible. This particular message symbol which has probability, most probable symbol which has probability less than 1/3, we will show that it is not possible for it to be assigned a code word length of 1. Hence we will prove that it requires at least a code word of length 2. So we start off with, so let us assume that C1 is our this message symbol which has probability given by P1 which is less than 1/3, and without loss of generality we are assuming, so we are assuming that this has a code word of length 1, and without loss of generality we are assuming that code word is 0. Okay. So what we are seeing is a situation like this. So we have a binary tree and this message symbol is assigned a code word C which is basically 0. That's what we are saying. And this has probability P1 which is less than 1/3. Now if this is so, then let's draw this tree again. So this is corresponding to 0 which is C1 which has probability P1 which is less than 1/3. So then if you look at what is the probability of this node, if this has probability less than 1/3, then this particular node has probability greater than 2/3. And how was this node formed? This node must have been formed using by combining some other nodes. So if this has probability greater than 2/3, and there are two nodes or leaves which are merging here, so at least one of them then must have probability greater than 1/3, right? If this particular node has probability greater than 2/3, then at least I am calling this as C10 and calling it C11. So at least One of them, either C10 or C11, has probability greater than 1/3. Correct? Now if that is true, then we can obtain a better code by interchanging the subtree of the decoding tree beginning with 0 with a subtree beginning with 10. Now what are we saying? We have a situation like this. We are saying this is the most likely symbol which has been assigned a code word of length 1, and this says probability P1 less than 1/3. But we just now found out if this thing has to hold, this particular node should have probability greater than 2/3. In other words, this particular code C10 or C11, either of them should have probability greater than 1/3. Now if that is the situation, then we can reduce the expected code word length by interchanging C1 with C10 or C11, whichever has probability greater than 1/3, right? So that's what I am saying, that we can obtain a better code by interchanging the subtree beginning with 0 with the subtree beginning with 10. Why? Because one of these nodes have probability which is greater than 1/3, whereas this one has probability less than 1/3. So if we do this interchanging, we are reducing the expected code word length. Okay, because this, either this or this, has probability 1/3. If we assign them code word length of 1 instead of 2, and we assign this code word length of 2 instead of 1, then expected code word length is going to decrease, because this C1 has less probability than one of these. Okay. So what we have shown then is this assumption that this message symbol, which is the most probable message symbol, if it has probability greater than 1/3, then we cannot assign it code word of length 1, because we just now saw that if that is the situation, we can actually get a better code by interchanging C1 with either C10 or C11. Hence we have proved that this symbol, which is most probable symbol, which has probability less than 1/3, must be assigned a code word length of at least 2 for a binary Huffman code. So as I said, this improvement contradicts the assumption that the most probable message symbol should have code word length 1, and hence we have shown that this most probable message symbol, which has probability less than 1/3, must have a code word of length at least 2. It cannot have code word length of 1. Now next example is on variable to block length coding. Now there is a variable to block length coding called run length coding. Now what does run length coding does? So let 0 raised to power n1 denotes a sequence of n zeros followed by a single 1. So this is a run of zeros of length n followed by 1, that is the sequence, and that's how we encode. So this run length coding works as follows. So for run length coding of block length of n, the message, which is a run of n zeros, is encoded into a code word of length n, and which is essentially a binary representation of the integer n, for where n lies between 0 to 2 raised to power n minus 1, and all zero sequence is encoded as all ones. So that's how a run length coding works. So any sequence of the form this is encoded into a sequence of length n, which is basically binary representation where n lies between this, and if you have a run of all zeros, this is encoded as sequence of ones of length n. So let us consider we have a source which emits zeros with probability 0.9 and which emit 1 with probability 1. So we are considering a discrete memoryless source and a binary source. So it emits zeros and ones. Now the question is as follows. Find the smallest n such that run length coding scheme is not a Tungsten message set. Okay, we need to find the smallest n such that this run length coding which we described here is not a Tungsten message set. The next question is, as a function of this n, find this ratio of output code word length, which is n, divided by input expected code word length of the input, which is expected value of y. Find out this ratio as a function of n. And the third part is find out a value of n which will maximize this efficiency. In other words, find out a value of n which will minimize this. Okay. So the first part is find out the smallest n such that the run length coding scheme is not a Tungsten message set. So in a Tungsten message set, what do? We do Q extensions of the extended root, and each time we extend the most likely leaf. That's your Tungsten message set, right? And how many such extensions do we do? If you recall, the number of extensions that we do is given by this expression. So it's floor of d raised power n minus k divided by k minus 1, because when we are extending a leaf, we are creating from the extended root, we are creating k new leaves, but one leaf becomes a node now. So at each time we are actually adding k minus 1 new leaves. So number of extensions that we would require to create a Tungsten message set is q, which is given by this expression. Now in this example we are considering binary code, so k is 2, d is 2, and our input takes zeros and ones, so k is also 2. So in this case the number of extensions comes out to be 2 raised power n minus 2. So in run length coding, what are we doing? We are doing basically n runs of zeros followed by 1. So in run length coding, the least probable intermediate node will have probability p dash given by probability of 0 raised to power q, because in a run length coding we are having n runs of zeros. So if we want to find out whether this run length coding belongs to a Tungsten message set, then every time we are having a run of 0, that particular node should be the most likely leaf. So if we are doing q extensions, the intermediate node has probability p dash, which is given by this probability, and probability of 0 is given by 0.9. q we just calculated is given by this expression. So this probability is given by this. Now for it to be a run length coding, every time basically we are extending run length coding, every time we are having runs of n zeros. So this probability p dash, if this probability is smaller than PU, then according to Tungsten lemma, we should have extended P of UI, BU1. If this intermediate probability P dash becomes less than probability of U being 1, then according to Tungsten message set construction, we should have extended P of U1. So, but then that would have been against the rules of run-length coding, because in run-length coding we extend zeros, we have runs of zeros and n runs of zeros. Okay. So then run-length message set is no longer going to be a Tungsten message set if this intermediate probability becomes less than probability of U equal to 1, because if this intermediate probability becomes less than probability of U equal to 1, then according to Tungsten lemma we should have extended the node or leaf corresponding to U equal to 1. So if the intermediate probability becomes less than probability of U equal to 1, in that case our run length message set is no longer going to be a Tungsten message set. And what is this intermediate probability? That intermediate probability is given by this, we have just calculated, and probability of 1 is given by this. So after simplification, what we get is n should be greater than this. That means if n is greater than 5, then run length coding is no longer going to be a Tungsten message set. Okay. So for n less than 5, n less than n 4, 3, 2, those for those values of n, run length coding for this particular source is going to be Tungsten message set, but for n greater than equal to 5, this for this particular source the run length message set is not going to be a Tungsten message set. Now the next part of the question was to calculate the ratio of the output code word length to the input expected code word length. Now how do we find out the input expected code word length? We can invoke the path length lemma to find out the expected value of y. We know that this is nothing but sum of probability of all nodes including the root node. So root node has probability this. Now next node, because you are in run length coding, you are extending the node corresponding to branch corresponding to U equal to 0. So if I draw the run length coding, it would be like this. So initially you have, this is 0 and 1, this is probability 1, this is probability 0.9, this is probability 0.1. Then again you are extending this. So this is probability 0.9 into 0.9 square. Then again you extend this, this will be 0.9 cube. So this you will do until the Q extensions of this leaf containing this 0. So the expected code word length in case of this run length coding can be written like this, and this can be, this is equal to this. Now then the expected, this ratio of n divided by expected value of y comes out to be this. Now the third part of the question says, what is the value of n for which we get maximum efficiency? And of course we will get maximum efficiency when this ratio is smaller, because we want to compress large block of data into, we are doing, remember we are doing variable to block length coding, so the output block length is fixed. So we will get more compression if we are able to combine larger blocks of data into this block of length n. So we evaluate this ratio for various values of n. I have written it here. For n equal to 1, this is 1. For n equal to 2, this comes out to be this. So you can see this ratio is smallest for this quantity. So in other words, we can say that for n equal to 4, this expected ratio is of n divided by expected value of y is minimized. In other words, the efficiency is maximum for n equal to 4. So let us look at the next problem. We have a discrete memoryless source that emits statistically independent binary bits with probability of 1 given by 0.005 and probability of 0 given by 0.995. So most of the time it is emitting zeros. The digits are taken 100 at a time and a binary code word is provided for every sequence of 100 bits. So we have a binary discrete memoryless source which is emitting zeros and ones, zeros with this probability and 1 with this probability. We are taking 100 bits at a time and we are assigning a code word. Now assuming all code words are of same length, find the minimum length required to provide code words for all sequences containing 3 or fewer ones. So clearly you can see that most of the most typical sequences which comes out of this source are going to be the ones which contains all 0 sequences, right. So we are providing code words to all sequences which have length number of ones 3 or less. Okay. So the question asks, what is the minimum length required to provide code words to all sequences which has 3 or less 1, and we are assuming that all code words are of same length. So that is the first part of the question. The second says, calculate the probability of observing a source sequence for which no code word has been assigned. Now when will no code word be assigned? When we get among these 100 bits number of ones which is 4 or more. In that case we are not assigning any code words. So the second part of the question asks us to calculate this probability, and the third part of the question says, use Chebyshev inequality to bound the probability of observing a source sequence for which no code word has been assigned. So in part B we are going to compute that exact probability. In part 3 we are going to use Chebyshev inequality to get an upper bound on that probability, and we will compare that probability with the actual probability that we will compute in part 2. So remember, we are considering these binary sequence 100 bits at a time. So what is the number of such sequences which has 3 or fewer ones? So this is number of sequences which have all zeros, this number of sequences which have 1 1, this is number of sequences of length 100 which has 2 ones, and these are number of sequences of length 100 which has 3 ones. So this total comes out to be this. Then the required code word length in this case is going to be 18 log to base 2 of number of such code words. Okay. So we can represent all sequences of length 100 which is coming out of this discrete memoryless source using a code word of length 18, assuming we are assigning code words to all such sequences which have 3 or less ones and all code words are of same length. Now when are we going to assign a code word to a sequence of 100 bits? Whenever we get a sequence which has either 0 ones or 1 1, 2 1 or 3 1. So let us compute the probability that the 100 bit sequence has 3 or fewer ones. So this is the probability of occurrence of 1, this is the probability of occurrence of 0. So this will give us the probability that I errors have this is the probability that I number of ones are there in the sequence of 100 bits. So this will give us the probability that there are I ones in the sequence of 100 bits. Since we are interested in finding the probability that there are 3 or fewer ones, we sum it over all i's going from 0 to 3, and this probability comes out to be 0.99833. So in other words, probability that we are not going to assign any code word to a sequence of these 100 bits is given by 1 minus this, and this probability comes out to be 0.00167. So this is roughly of the order of 10 to minus 3. That's the probability that we are not going to assign a code word to a 100-bit sequence. Recall that we are assigning code word to all 100-bit sequence which has all zeros or at least 1 1, 2 1 or 3 ones. Okay. Next we are going to use Chebyshev inequality, which basically says that if Sn is the sum of n IID random variables, then probability that the absolute difference between sum and n times mu is greater than or equal to epsilon is given by n times sigma square by epsilon square, where mu is the mean of xi and sigma square is the variance of xi. So in this problem our n is 100, mu is 0.005 and sigma square is 0.005 into 0.995. We are interested in knowing that the sum is sum of ones is basically greater than or equal to 4. So we choose our epsilon in such a way such that our sum of these 100 bits comes out to be greater than or equal to 4. So for the given value of n and mu, our epsilon should be chosen as 3.5. Then only we will get this condition that sum of this 100 bits has more than 3 ones. So in this particular case our epsilon should be chosen as 3.5 for the given n, which is this, and number of mean of this 0 is basically 0.00. This mu is mean of this number of ones is 0.005. So epsilon, if we choose to be 3.5, we get the condition that sum of these 100 bits has more than 3 ones. So if we plug in the value of n, sigma square and epsilon, which is 3.5, in here we get the condition that sum contains 4 or more ones. That probability comes out to be upper bounded by 0.04061. Please note that this is actually quite a loose bound, because the exact probability comes out to be 1.67 10 to minus 3, whereas this upper bound is 4 into 10 to minus 2. So this upper bound is quite loose. Okay. Finally, we are going to show you that a typical set is essentially the smallest among all the sets that have non-negligible probability. So let us consider a memoryless source U, which is emitting these random variables ui's, and these are IID distributed. Let un denotes an n tuple. So u1, u2, u3, un, that's an n tuple that is denoted by un, and its probability is given by p of un. And since it's a discrete memoryless source, we can write this probability of un as probability of ui and product of over I going from 1 to n. Now let delta be greater than 0 and B is a subset of this un where the sequence satisfies this condition that the cardinality of Bn is less than equal to 2 raised to power n into h of u minus delta. Then we want to show that as n tends to infinity, probability that un is in Bn is basically goes to 0, which essentially will show that typical set is essentially the smallest set which will have non-negligible probability of occurrence when n asymptotically when n goes to infinity. So let us prove this. So we consider a typical set with epsilon we choose as delta by 2. Now let's say you have two sets A and B. Say two sets A and B, right? Now if I ask you to write B, you can write B as, so what is B? B is this, right? B is this set. This is B, right? Now what is B? B is this portion plus this portion, right? So I can write B as B intersection A union B minus this set A. So that's what I am writing here. I am writing this Bn as Bn intersection this typical set union B minus this typical set. So probability that un belongs to Bn can be then written as probability that un belongs to intersection of Bn and this typical set, and probability that un belongs to Bn minus this typical set. So this is nothing but complement of typical set. Now we know that from the property of asymptotic equipartition property, we know that as n goes to infinity, this probability is negligible. This was very, very small, some epsilon, so this goes to 0. Okay, so as n goes to infinity, this probability basically will go to 0 as n goes to infinity, right? So limit when n goes to infinity would be then upper bounded by limit when n goes to infinity this probability. Now what is this probability? This probability can be upper bounded by summation of this p of un, where un is in intersection of Bn and this typical set. Now this can be written as, now cardinality of Bn is, just a second, so this one, if you go back, this Bn is less than 2 raised to power n h of u minus delta. So the probability can be basically upper bounded by 2 raised to minus n h of u minus epsilon, and summing over this particular set, right? Now when I summing over this particular set, I can write this as greater than or equal to cardinality of this set multiplied by this probability. Now this probability, if you recall, from the properties of typical sequences, we know what is the probability of a typical sequence, that is upper bounded by this quantity, right? That's what, from here to here we get this relation from the property of typical sequence, that probability of un when u basically belongs to a typical sequence is upper bounded by 2 raised to the power minus n h of u minus epsilon. And this we are summing over this particular set and this particular set. So this would be cardinality of Bn multiplied by this. And what is Bn? Bn we just now saw is given by 2 raised to the power n h of u minus delta. So if I plug in this value of Bn, which is 2 raised to the power n h of u minus delta, and plugging the value of delta, which we chose as delta we chose as 2 times epsilon. So epsilon we chose as delta by 2. So if I do that, then what I get here is 2 raised to the power minus n into delta by 2. Now if I take limit now, n goes to infinity, this term will essentially go to 0. So which essentially proves that typical set is the smallest set which will have a non-zero probability. So with this we will conclude this lecture. Thank you.